Hello everyone, I'm Shujian, a new faculty member at the UiT, the Arctic University of Norway. The title of my presentation today is Information Bottleneck Approaches for the Understanding of Deep Neural Networks. This is a joint work with my supervisor, Dr. Jose Principe at the University of Florida, and my co-supervisor, Dr. Robert Jansen. I was a PhD, and I also appreciate the collaboration with my colleague, Dr. Lewis from the University of Kentucky. So we know that currently the deep neural network has achieved overwhelming performance in different areas, including, for example, the self-driving car, the speech recognition, the energy analytics, as well as the healthcare applications. However, there are only a few theoretical understandings to their behind their success. So there are several open problems still and fundamental problems still behind the deep neural net. For example, the interpretability, what there are already two experts just mentioned. For example, how can we identify the most relevant features or component in the input to contribute to our decision, or if it is possible for us to explain why did a trained deep neural net reach a certain decision. And all of such issues are concerned or related to explain or understand deep neural networks that are already trained. However, at the same time, we also want to have a way to understand or interpret a deep neural network when it was trained from scratch or from the initialization at the end of the training. And in such cases, we also want to understand, for example, why did a deep neural net perform very well, or how to improve the generalization ability of a deep neural net to out of distributed data, or what impact has the depth of a network. So with so many open problems in either interpretability or around the generalization, or so because of some open problem, many people also blame that a deep neural is a black box. So what we did in the last few years, just want to open the black box of deep neural networks, either on interpretability or in the generalization, from the perspective of information theory. Now, I want to say that the information theory, although it's originated from the physics or from statistics or mathematics, but the general idea of information theory has gradually become a popular topic in the explainability of interpretability of deep learning. And for example, there are several appealing achievements from information theory to help us to understand or opening the black box of deep neural networks. For example, with information theory, we can now identify the most influential features or data to the decision. We can also use the tool of information theory to understand the generalization behavior of deep neural network behind the training process, and also explore or derive or identify some fundamental properties. For example, the generalization bound behind the different deep neural algorithm. We know that the generalization bound is a key to design the next generation of machine learning models. And at the same time, we can also use information theory to understand the inner working mechanism of networks such as convolutional neural net and other kinds of neural networks. For example, the dependency of different neurons or the dependency of different layers. So in this talk, I only want to briefly introduce some of the works from our group in the last few years. And because of the limited time, I will just introduce two aspects. The first is that how we developed a new way to quantify information theoretical quantities from data. And the second is how we apply the theory of information bottleneck to understand a deep neural network or to improve its practical performances. So before presenting our methodology, I just give a very quick review of the classical information theory from under the classical Shannon's entropy functional. We know that the entropy is usually defined as the negative of the expectation of the log px, and here px is a distribution of variable x, and the divergence and the commonly used K divergence can be understood as a way to quantify the closeness or distance of two distributions px with respect to qx. And at the same time, we also have mutual information, which can be understood as a shared information between two variables x and y. And mathematically, the mutual information is also the equivalent to the KL divergence between the joint distribution pxy with respect to the product of their multi-distribution px and py. And we can see that those are definitions from the classical information theory from Shannon's entropy functional, and all the quantities are defined over a probability space. However, in order to successfully apply the definition, for example, the entropy or the mutual information to current existing machine learning applications, the first step we know is that we should have a way that such that we can precisely estimate such quantities. For example, given a group of data, how we estimate the entropy, or given two groups of data, how we estimate their divergence or distance, or how we estimate their mutual information. The thing that we know that all the quantities are defined over probability space. However, in machine learning, we know that in most of the cases, our data is in a high or even ultra high dimensional space, which means that if we still stick to the Shannon's entropy functional definition, the first step we need to do is to maybe have a way to estimate the density of the data px or qx at first. But however, because as I just said, in machine learning, in most of the cases, our data is in a high dimensional space. And we all know that the density estimation in high dimensional space from a statistical perspective is infeasible or intractable. So the first question is that how can we still use the definition of mutual information or divergence, but flexible in machine learning problem, or is it possible that we can still estimate the information theoretical quantities without resorting to the estimation of the underlying data distributions? If so, then we know that if we can avoid the density estimation but still get the quantity of divergence or mutual information or entropy, then some problem can be significantly simplified. And this is also our key motivation to develop a new information theoretic quantities without resorting to the estimation of the underlying data probability distribution. And in the last few years, we give a positive answer to these questions, and we call our estimators the matrix-based entropy functional. And our general idea is to show that it is possible to define mutual information or divergence or entropy just over the eigenspectrum of positive definite metrics that are generated from given samples. For example, in the traditional definition, Shannon definition, if we want to give a group of data, if I ask the question how to estimate the entropy or total uncertainty associated with our data, usually what we need to do is to estimate the probability distribution px and put it into the formula of the negative of px log px and the integral. However, in the new matrix-based entropy functional, what we did is just first, given n samples x1, x2, and xn, each xi is in a d-dimensional space, and d is arbitrary number. And the only thing we need to do is to first compute a gram matrix which is of the size n by n, and we show that the entropy or total uncertainty associated with the group of variable, the variable x, it can be exactly defined over the eigenvalues of the normalized gram matrix A. And the formula is, we can see it's very, very simple, and it's also easy to compute. And mathematically, we also extend the matrix-based entropy to show how to define the divergence between two distributions or define the mutual information between two variables or even more than two variables. And we also show that such definition is differentiable, which means that it can be directly put as a loss function to train deep neural networks as you wish. Now, with one of the state-of-the-art estimators in mutual information or divergence, especially in high-dimensional space, our next step is to use information bottleneck theory to try to understand the training of deep neural networks or to improve its practical performances. As a background, the theory what we use is called the information bottleneck, which is can be understood as a repetition learning principle. It's easy to understand. Given the input data X and the desired output Y, for example, the classification label, and we want to learn a compact repetition T. So the information bottleneck formulates the learning process as a trade-off between two items. The first item is to maximize the mutual information between T and Y. This is easy to understand because we want to use a T for our predictive tasks. So definitely we should maximize the mutual information between T and Y such that we can guarantee a good predictive performance on tasks Y. At the same time, we also want to minimize the mutual information between X and T. And this is the purpose of the minimization between the mutual information between X and T is some that we want to learn a compressed or compact representation that does not have redundant or noise information in the original input X. So this explains why we need to do the trade-off. First, we want to maximize the mutual information between IY, the output and the T. At the same time, we also want to have a small mutual information between X and T. And mathematically, these two trade-offs combined together can be understood as a natural approximation to the minimum sufficient statistics. So this is the background of information bottleneck. So based on this principle, and also coupled with the state-of-the-art mutual information estimators, especially in high-dimensional space, then we try to understand the learning, the learning behavior behind the deep neural networks. So what we did is that we plot an information plane. In the x-axis of the information plane, it's a mutual information values between X and T. Here, T is a latent representation of deep neural networks, and the X is the input, and the Y-axis is a mutual information between the label and the latent representations, and the dark blue points or even black points at the bottom of the image is a mutual information values at the beginning of the training, which is just a network just after the initialization. And the green point shows the mutual information values in the middle of the training. And the yellow points shows the mutual information values at the end of the training. And we can observe clearly from this figure, there are two phases associated with the change of the mutual information values. In the first stage, all the mutual information values xt and yt have a sudden increase. However, there is also the second phase in which the mutual information values, especially the mutual information value between x and t, is decreased, and we can interpret this as a compression phase. So, what does this figure tell us? It told us that when we train a deep neural network from scratch, from the beginning initialization to the end of the training, the latent representation will first fit in the data such that the mutual information values will increase. However, when the training is okay, the latent representation begin to drop out the redundant information in the X, which means that the deep neural network has a natural compression phase, and those compression phase can somewhat explain or give some insights on the prediction on the generalization performance of deep neural. Why deep neural network can have the ability to generalize, because maybe there is the existence of the compression phase. Currently, this is there is if the compression phase exists is still a controversial issue, And there are some groups at the US and also including us have lots of work in top journals or conference behind to have a whole discussion behind this topic. But currently, the mainstream of the community, academic community, still begin to acknowledge the existence of compression and feel that the compression can somewhat indeed give some insight to the generalization behavior of deep neural networks. However, what I just mentioned is just some theoretical understanding to the generalization of deep neural networks. But the idea of information bottleneck as a practical tool, it can indeed be flexibly used in real artificial intelligence applications, especially related to the interpretability. For example, in the left figure, I show a very popular problem in computer vision called the saliency detection or extract the salient regions. So now you can imagine the input is a full image of the cat in the background, in a black background, and the label, the classification label is Y, and this is a cat. So we can apply information bottleneck to learn a compressed representation T, and the T is the compressed representation that drops out all the irrelevant or all the noise information in the original input image X, but the T is sufficient for us to make the prediction that this is indeed a cat. So apply the principle of information bottleneck and formulate the learning as a trade-off between maximize the mutual information between IYT and at the same time minimize the mutual information between X and T. The T is somewhat originated from X, but it drops all the irrelevant information from X. And finally, we can see that the T is just can be understood as a mask or just a window only focus on the head of the cat, which it tells that if we want to make a good prediction about the X is indeed a cat, then our network should focus on the cat, on the region of the cat, the head of the cat. Similarly, we can also apply the general idea of information bottleneck to do the explainability in natural language processing applications. For example, if the input sentence is that I cough a lot at night, and based on this sentence, we want to figure out if I have a flu or not. Then in order to do this, we can just use the idea of information bottleneck to learn or to generate a binary mask, and such that after put the binary mask on the input data on the input sentence, we just keep the most informative words or most informative tokens that can help us to make the decision. For example, a well-trained network with the idea of information bottleneck can exactly identify from the sentence I cough a lot at night, just extract the two most informative words, only with the word of cough and night. Only based on these two words, we can make a decision if I flew or not. Similarly, currently our focus of attention also begin to gradually to use our theoretical understanding to the generalization and to improve the practical performance of deep learning, especially in the generalization performance. And in one of our recent work, we show that we can use information bottleneck to drop out spurious correlations that are especially associated with the background, and just use and only let our network focus on the causal attributes that are really contributed to our decision Y. And use such a program, we can use information bottleneck to progress drop spurious correlations and only learn causal correlations that are stable across the element. And use such a way, we can show that the information bottleneck can indeed improve the practical performance of deep learning in sequential element. And the conclusion is that we mentioned a very effective way based on the eigenspectrum of the positive semi-definite matrix to quantify the mutual information, the entropy, and the divergence only from data. And as application, we show that the general idea of information theory, especially the information bottleneck, can help us to understand the mechanism behind the deep neural net and also to improve the practical performance of deep neural networks. However, what I want to say is that there are many other and more opportunities just behind the information bottleneck. For example, there are information maximization, the rate distortion functional, and currently the rate distortion function has also been used to the extendability, and there are also principle of relevant information. So the opportunities are gradually become increasing.